See,
Oh,
I have this theory that if I go a week without learning a new cursed fact about set theory, I have wasted that week. So I've ticked that off this week.
You've restored your disequilibrium.
Right.
Very good. Okay, Ken, shall we get started?
sure. Give me 1 sec.
Yeah, I wanted to make one note before we get started. So we had a bit of a problem with voice chat last time. I hope it just has gone away, but in case it hasn't, can we make sure that we're muted when we're not asking a question in the audience? I think that seemed to help at the end of last lecture, so thanks everyone. All right, whenever you're ready, Kenneth.
Cool. All right. Cool. Yeah. So let's get started. So this is a second, I believe, lecture on algebraic geometry from Cox Little O'Shea, and I think I'll be following the book pretty closely. And the chapters, actually, I forgot what chapters we're on. I guess we're on chapter 1, and I'm going to start with this 1.4, I guess, on ideals, right? So I think Dan's already set up a lot of the conventions and notations that we'll be using, but in case I missed it and I kind of introduced notation without explaining, let me know and I'll rectify it. So as before, we let R equals the polynomial ring with n variables. So what I'll do is, instead of writing k open bracket x1 to xn, I'll just use R for the most part. It's easier to write, and we just have to remember that this is the polynomial ring in variables, and this is the only kind of ring we'll be dealing with, right? N might change from 1, 2, 3 up to an arbitrary n, but R would be just this polynomial ring, and K is a field. And I believe we talked a little bit about what fields are last week. And in case you are uncomfortable with fields, and you just think of this as real numbers, complex numbers, or rational numbers, they're all fine to substitute in your head. Okay, so the definition, we're going to start with the definition, and I'll go through and talk through what this means and some of the properties of these things. So the fundamental object that we'll be thinking about and talking about is an ideal. So I'll usually use the capital letter I to denote the ideal. This means a subset. So an ideal, so a subset of R is an ideal if the following is satisfied, are satisfied. So 1, right? You know that 0 is in the ideal. Of course, 0 is, when I write 0, this is the 0 polynomial in R, as opposed to the 0, I guess, a 0 number in the field, 0 elements in the field. So next, if you've got 2 members of the ideal, right, and what this means is that the sum of these 2 elements are also in the ideal. So the ideal is closed under addition. And 3, right, if you have R in R, so this is just an arbitrary polynomial. So maybe I should use P, but I use R here. But this polynomial, and F is in I, then the product is in I. So one way of thinking about another way of thinking about this is ideals. We're talking about ideals in this particular polynomial ring, but in general, right, you can think about ideals in other rings as well. I guess Dan kind of alluded to this, the general concept of a ring last week, but the integers are a ring, and you can kind of convince yourself that the multiples of any integers also is an ideal in the ring of integers.
It's kind of weird to have
that's another way.
0 in I, right? So this follows from 3. I don't know why.
Yeah, I actually think, when I was reading through this, you didn't need all of these, but maybe, yes, it does follow from 3, and so maybe we don't need this. Let me just cross it out, just with a different color, right? We don't really need this. So, if you need to check something's an ideal, right? 2 and 3 suffice, but I guess it's there as an explicit condition in any case in the book. So, okay. So, an alternative way of saying this, right? So, alternative is that
Oh
I
wait,
is an
doesn't one exclude the empty set from being an ideal?
yeah, I guess it does, doesn't it? Yeah. Is it possible to Yes, not. Thanks. Oh yeah, I should say I.
0 in I. Sorry, Ken. Yeah.
Yeah. Thanks.
By the way, I don't think it's attached as speaker because I got
Am
the
I not?
prompt to.
Am I not attached as speaker? I'm sorry.
Oh, sorry, I got the prompt to attach the speaker, so I assumed that meant that no one was. Sorry.
You can kick me off. Maybe you can give the lecture.
Yeah, I'll just pick corrections.
Oh, that's funny. So, as I was saying, another way of saying this in a more succinct way is that I is an ideal if I is a k-linear subspace of R and 3 holes. So I guess I didn't write it like this because we didn't really talk about vector spaces, and I wasn't sure whether that was a prereq. But if you know about vector spaces or linear subspaces, right? Yeah, if basically ideals are linear subspaces such that they're closed under multiplication by any elements of R, any polynomial multiplied by elements of the ideal, land back in the ideal. So usually, when we introduce new objects in mathematics, we want to talk about some methods of constructing them and give some examples, and then we talk about some properties, some basic properties that these objects have, and so we'll do that. Sometimes mathematical objects are somewhat difficult to construct, but ideals are not super hard to construct. But nevertheless, we'll talk about how it relates to varieties, which is the other kind of central object that we want to study in algebraic geometry, besides ideals. Okay, so some examples or some ways of constructing it, right? And we'll start with some elements of R. So I'm going to call them F1 to Fs, right? So I'm going to use S to denote just this arbitrary number of elements, right, as opposed to N, right? I'll reserve N as the number of variables, and S will be for these guys, right? So the ideal generated by F1 to Fs is defined as follows and denoted as follows. And denoted as follows. So I'm going to deviate a little bit from the book's notation. I know this is probably not the best thing to do with teaching from a book, but I've written ideals like this for so long now that it feels strange to use any other notation. I don't know if Dan has an opinion on this, but I usually use round brackets or parentheses to denote a bunch of elements generating an ideal, whereas the book...
I'm the same. I find the book's notation kind of weird here. It's also standard. So either is fine for you to use.
Yeah, I guess angle brackets are harder to write on a board. So, parentheses.
Oh man, our lives are so hard.
Is that... Oh my god. This is all going to be on YouTube at some point, right? People can laugh at this. It'll be hilarious. So this is maybe not the book's notation, but this is a notation I kind of like. Whenever you write R, which is the ring, which is maybe is a set, right? But it's a ring, it's a polynomial ring. So when I write RF1, what I'm saying is that I want to RF1 is a set, right? It's gonna be I take every element of R and then multiply by F1. I guess here on the right, but since everything's commutative, it doesn't matter. And so it's a shorthand of writing, kind of a set. Kind of translated by F1 by multiplication, by right multiplication, and the book will tell you that this is, if you expand everything out, F1 plus RSFS, right? So it's all of the elements, right? Linear combinations of these guys, right? Where R1, RS are elements of R, right? So so this is what we mean by an ideal generated by a finite number of elements, right? And so we have to prove that this is an ideal, but I think this is one of the exercises. I don't know whether I assigned it, but at least when I prepared the notes, I did write this down as an exercise. So I guess if I didn't assign it, I'll assign it now. So lemma 3. Hopefully this 3 is the 3 from the book, right? Maybe this is I wasn't very diligent about keeping track of numbers of lemmas, and maybe if this is wrong, I don't know. I don't have any Robux, but I guess if I make a mistake, does Dan pay out? I have no idea.
What? This is not a good convention.
I'm kidding. No. I'll buy some Robux. I'll buy some Robux if I need to. It's an ideal. Okay, so I'll leave the proof as exercise. I think this is not too hard. So basically, we have to go back to the definition and check those 3 conditions, or 2 conditions, if we accept that such a thing is an empty. And so so this is probably something that we would have done as undergrads when we studied, like vector spaces. Checking something is a vector subspace is a very similar kind of exercise, right? Okay, so one way of understanding this definition is looking at systems of equations, right? So you're given F1 to Fs, right? You might think that, well, the system of equations, F1 equals 0, F2 equals 0, and then Fs equals 0 has something to do with this ideal, and that's correct, right? So let's spell out how this works. So this is related to the system of equations. After all, we are interested in solving polynomial equations as main kind of objective of this course, and I believe Dan's talked at length about what it means to write down, a system of equations. So I'll just write down such a thing without comment. Fsx equals 0. So maybe I'll say another thing. When I usually write F1 to Fs in R, I won't write the function, I won't write the arguments in there because I'm really thinking of them as polynomials. But if I'm, writing down a system of equations, I'm going to write F1, comma, open bracket, x, close bracket equals 0 to indicate that, x is the variable that we're talking about. The other thing that I'm going to be a little bit maybe negligent, maybe that's not the right word, but I won't write x1 to xn, right? I'll just write x to indicate that this is an argument with n components, right? So this is really, we did mention that, these are all polynomial rings of R, and R has n variables. So this is really a system of S equations in n variables, right? So this is a system of equations in or system of S equations in n variables, despite what it might look like with the x in the slot for the argument. So let's walk over to the next board. Okay, maybe I'll move over. Maybe I'll stay. Okay, that's fine. Okay, so I think so where was I? So in my notes, I see there's a typo on page 31. So I've totally forgot what that was. So I'm going to write this down. Fix the typo in the example on page 31. Okay, this is somewhat mysterious. I actually don't have the book open in front of me, so I don't know what that is. It's probably to do with a subscript or something like that. So also I'm using possibly edition 4. There were two editions, I believe. Dan was saying something about how the exercises were numbered differently. So I believe this is the latest edition. Okay, so yeah, so I'm gonna move on from this because I actually don't remember what the typo was. But you can find it and tell me later on. So an ideal is finitely generated. My stylus is not behaving. Finite generated if there exists elements f1 to fs, right, such that I is equal to f1 to fs. So the method of constructing ideal earlier only gives us finitely generated ideals, and that's all we've seen so far. But we're saying that, well, you know, an ideal is finitely generated if it can be written in this form. The implication is that there may be ideals that are not finitely generated. Is someone drawing on my board, or is that my board going crazy? Right. So there are ideals that are not finitely generated, but this is probably a point of interest in the course, is that maybe one of the things that we'll prove is that in the polynomial ring, in a finite number of variables, that all ideals are finitely generated. Okay, so this definition, well, we have to make this definition because in other rings there may be non-finitely generated ideals, and I think in the exercises there are some examples. So I'll make another note here. The book calls this thing a basis. So the book calls this a basis. I typically don't call this a basis. I usually say this is a generating set or a set of generators. But I guess, yeah. Yes, a basis for I, right? So for I. Now, the reason why I don't like basis is because we also use the word basis for vector spaces. And so that might give us the wrong mental image, right? So these generating sets or basis for I are kind of different from bases for vector subspaces. So, so yeah, yeah. So you know, they may not be unique, right? And of course, you know, bases for vector spaces are also not unique, but you know, you may have different numbers of generators for the same ideal, right? And so not even the number of things can be well, I mean, I guess, yeah. So like for a vector space, right? If you have an n-dimensional vector space and you have like a basis, it has to have n elements. You know, if you have more than that, you can still span the vector space, but you no longer call it a basis. But then here we kind of call all generating set spaces, so it's kind of strange to use this terminology. So I tend to avoid it. But then basis is also much shorter to write than generating set. So I might actually break my own rule and call it a basis. But anyway, bases and generating sets are the same thing for ideals. So one of the goals for this course, so one of the goals of the course, mag, right, is to describe useful basis, well, describe a useful type of basis for any given ideal, right, is to give a procedure or an algorithm, or give a description of, say, an algorithm for a special basis for any ideal in R, right? Well, I should really have said ideal. So there's a piece of notation that I didn't introduce, and maybe the book doesn't introduce. I'll maybe do it here. This is ideal, right? So this means I is an ideal in R. Little triangle. Maybe I should draw this as a triangle. Right. So this is. I don't think the book uses this, but I'll use it because it's short. All right. So give an algorithm for a special basis of any given ideal, called Grobner basis.
Is this an algorithm to find the basis?
Yes, to find a basis,
Right.
which is so even Grobner bases are not unique, right? But they have better uniqueness properties than just any old basis. So I guess this is another argument for calling it a basis, because we are calling it a Grobner basis, not a Grobner generating set. So, you know, maybe it's not so bad to
Reduced
to
bases are
use
unique, so there is a sense in which reduced Grosvenor bases, I would kind of
Right,
think,
right.
deserve to be called a basis in some sense.
Yeah, that is true. So yeah, we can kind of use that terminology for Grabner basis. Okay, so we'll use this to show that every ideal of R is finitely generated. I've kind of mentioned this. We'll prove this using Grabner basis in this course, and that's called the Hilbert basis theorem. So we'll use this Grabner basis to prove the Hilbert basis theorem, which says that every I R is finitely generated. So I'll use F dot G dot to to abbreviate finitely generated. It's a common abbreviation. So yeah, so this is actually a nice proof using something that's quite explicit. The proof I learned when I was a student does not use Grabner basis, so I actually never learned Grabner basis when I was young. And this is actually I like this proof. I don't know if I like it better, but certainly it's refreshing to see something done in a computational way, using an algorithm that you can compute reasonably for small numbers of variables, by hand, right? So it's satisfying to see this. So there do exist ideals. I have another comment here that expands on what this means, but maybe I'll leave it just because we will talk more about this when we get to the chapter on Hilbert basis theorem. But basically, what this means is that maybe I will make a small comment, because the next comment really is about when ideals can be potentially generated by infinitely many generators, right? Now, if you pick, right, an infinite number of elements of R, you can reasonably say that the question here is, of course, right, if we have F1, F2, all the way up to whatever, right? So this is like some infinite set, right, of things in R, right? And we consider the same thing as we did before, which is this this sum, right, of, you know, I'm going to use J as the index set, Ri, F. Maybe that wasn't the best thing to do. Maybe look at this guy, R1, Ri is in R, right? Is this finitely generated, right? Is this finitely generated? So in other words, do we need all of these infinitely many F1, F2, all the way up to F, you know, I guess in this index set J, do we need all of these generators to get every element of this set, or can we throw out all but finitely many of them? And I guess that's the other way to say it, right? You know, Hilbert's basis theorem says yes, you can throw out all but finitely many of them, and this set that we've written down here, or this ideal, is actually you know, has a finite basis. So let me just say that this is a F I in J. These dots here make it kind of unclear what I'm talking about. So what I really mean is that, yeah, this set here, I should have written in red, right? The index is indexed by this set J, and J could be, you know, J could be infinite, right? Okay. Okay, give me 1 second. I seem to be unable to. Something's wrong with my app. Give me 1 sec. Okay, let's go to the next one. I guess I don't have to move to the next board, but I'll move over anyway. Okay, so yeah, so let's look at an example where there may be, you know, an infinite number of generators, and we have to keep all of them, right? Now, I did say that we'll be looking at polynomial rings and a finite number of variables only, but I'm going to break that just for this example. So this example possibly is in an exercise. So there do exist ideals which are not finitely generated. Not finitely generated. And I guess, strictly speaking, I didn't define ideals in general. I kind of just defined it for the polynomial ring and a finite number of variables, but the definition is, you know, doesn't use any properties of the polynomial ring, right? It's just some closure conditions on multiplication and addition. So you can really, that definition is actually a general one, right? So if we consider
you better write down here, like, not in a polynomial. Oh, you're going to give an example. This example coming straight after the previous two remarks seems a bit contradictory.
What did I say? Oh yeah, I did. Yeah. So yes. So yeah, no. So this is not a polynomial ring, right? So previously, those remarks all, you know, they all pertain to R, which is this polynomial ring, finitely many variables. And here I'm gonna go outside of that, write down a polynomial ring with coefficients in the complex numbers, right, with an infinite number of variables, just like, I guess, indexed by the natural numbers. And so this guy has an ideal which is not finitely generated, right? And so and we're going to just write, well, you probably guess what this may be, right? You just write, and you just do this for every single variable there. And so so the exercise is that this is not finitely this is not finitely generated. So yeah, so I is not finitely generated. And as Dan pointed out, right, this is not contradicting what I just said, right? Hilbert's basis theorem is a theorem on polynomial rings with a finite number of variables, right? So let me just make a note here. Hilbert basis theorem is for finite polynomial rings, polynomial rings with finitely many variables. So this is not a contradiction.
Yeah, I think it's probably safe to adopt the convention that for us, polynomial ring means finitely many variables, right? So we're just kind
Right,
of
right, right.
breaking that convention for a moment to point out that you can talk about polynomial rings with any set as the index set for the set of variables. We won't do that, but if you do, then you get things that aren't necessarily finitely generated.
Yep. Cool. So yeah, so this is a nice example. I don't know whether this is one of the exercises where we want to prove that this is not finitely generated, but I mean, actually, I think it is. I just don't remember whether it was one of the ones assigned. But anyway, if you're interested in this example, feel free to take a look at it. So
Or just for Eleanor, take the polynomial ring where there's a variable for every ordinal. This is the category
Oh,
of
God.
modules over this ring has some interesting properties.
Could you please put that thing back where it came from, Dan? Let's not. I'm not gonna sleep well tonight. Thanks.
Most welcome.
what are the interest? No. I'll ask you later. So here's another proposition. Equal ideals define the same varieties.
We haven't
I
even
promise you, I will do.
we haven't even defined what the
I
variety
promise you, I
associated
will.
to an ideal is, have we?
That's a good point.
So last
I was gonna
time
say.
I defined the
You
variety
didn't use
associated.
it?
I did for a set of polynomials, a finite set. So there's no easy way of finagling
Yes.
that out of
Ideals. So the reason why it's written like that is because the book actually writes it out like this, right? And I got lazy and I just kind of paraphrased it. Maybe this is. Do I owe Dan some Robux? How do I get Robux?
Have me real money.
Real money. It's hilarious. Given ideals, I and J. I don't remember whether S and T were meant to be the same, but they may as well be whatever they are. If I equals J, then the variety. So we did define this, right? Did you do this double V thing? I don't remember.
No.
I
What
think
we
you did.
defined was V of the set of polynomials. So what you want to write there is if I equals J,
Oh, okay.
then V F1 dot dot dot
Oh,
Fs is
right.
equal to V G1 dot GT. Yeah.
Okay, yeah, with one. Oh, yes, that's right. That makes sense. Okay, so that's the statement, and I guess I promise I will prove something at some point. But I think these are actually these were actually exercises, perhaps in the book. So I'll leave them as they are, and we'll keep going. So I do want to end up talking about the division algorithm today. So I think I'll spend the time that I have to prove things on the actual properties of the division algorithm. Okay, so yeah, so we'll give an example. Let's move over to the other side or the other board, the other row of boards. Let's walk over there. So before I give the example, maybe it's a good point to it's a good time to kind of emphasize, right? Like the previous proposition is actually an important one, right? Given two ideals, you can construct systems of equations of those. I mean, if you have these generators, right? When I say ideals constructed as ideals generated by a finite number of polynomials, right? We can write down systems of equations with these generators, and these systems of equations, their solutions will define a variety inside some affine space, and so this is kind of the point of algebraic geometry is that you know, the ideals is on the algebraic side, it has some algebraic information. You can do algebraic operations on these ideals, like quotient out the ideal, the polynomial ring by the ideal to get another ring, right? We're not talking about that in this course, but that's a construction you can do. That's completely algebraic. You don't need to know about varieties to do that. But so, and then at the same time, you can take these ideals and look at the geometric side, which is to look at the zero set of these polynomials, and then you have a geometrical object with, you can study it using geometry. You can look at like its tangent space, for instance, right? Because it's actually a submanifold. Well, it's not quite a submanifold, but it's a subset of affine space, right? So you can use techniques from geometry to study it. And these two objects are, I guess they're more or less morally the same, right? The way we're doing it in this course, they're not going to be exactly the same because the varieties are they're missing a lot of information. But we can see some of where algebraic geometry, where we'll go in algebraic geometry, in this very simple basic proposition that equal ideals, define the same varieties. So an example here. And it's funny because I have an example, but I have no idea what the example is supposed to be demonstrating. But maybe I'll work it out as I write this down. So we're going to give an example of an ideal, right? Because we just talked about ideals. So we're going to write down an example of an ideal with two variables. So I'm going to be a little bit lazy about defining the polynomial ring that I'll be working in. But hopefully, because I'll label the variables, it's clear that this is going to be inside k, x, y. And I'm not going to define k as anything other than just a general field. So I'm gonna say that I'm gonna claim that x squared minus 4 and y squared minus 1 are in the ideal. All right, and so I guess the way to do this is, I guess we don't have a systematic way of eliminating variables yet, but you can already kind of see that you can subtract these two elements from each other to eliminate x squared and then subsequently eliminate y, just like how you would do linear equations, right? There are no lower order terms, it's x squared and it's y squared, and you can just treat them like, s and t, right? And so, in the same way that you can eliminate variables using linear algebra, you can eliminate x squared and y squared from the equations, and I get that x squared minus 4 and y squared minus 1 are both in the ideal. So I guess all I'll say is, you use, linear algebraic methods. We'll do this, we'll give you this. Okay. And so now the question here is, okay, so you've done some, linear operations on these, somewhat complicated generators to give you some simpler generators. Is it true that the ideal is generated by x squared minus 4 and y squared minus 1? So it'd be nice if it were. And I think this is actually an exercise. Again, this is exercise, I don't remember the number, but it's one of the exercises in this chapter. So I'll leave this as an exercise to get you to think about why this might be true. And so, I think, you all have some intuition for whether this is true or not. You're doing kind of very linear things, and you can go from the original set of generators to x squared minus 4 and y squared minus 1. You can go back using kind of linear transformations as well. So it's fine as long as, k is I guess, characteristic. Well, I guess R, C, or Q, I think we're fine, right? So
Let me
now,
interrupt
can you
and
prove a Sorry?
can somebody tell us what the variety associated to either of these two pairs of polynomials is? What does it look like over R?
Is it like points? Like
Yeah.
I guess there's two solutions for every polynomial, so 4 points.
Yep.
Uh,
Yeah, that's it.
okay.
Cool, thank you.
Yeah, good. A couple of people got it. Yeah, so, when we draw these varieties that look like pretty curves or like that rows or surfaces, but collections of points can also be varieties. There's a nice one of the exercises that was assigned, I believe, for section 1, sort of introduces that, and this is an example of that.
Cool, thanks. I think it's nice to have the diagram there. Right. So I think the other thing I wanted to say about this example is that I mentioned we can use linear algebraic methods to kind of do this. Can you prove a more general statement about invertible linear transformations acting on ideal bases? Sorry. So I'll leave this as maybe extension. General statement about, I'll leave it somewhat vague, invertible linear transformations acting on ideal basis. Okay, so I am using bases, I guess. Okay. Okay. So yeah. So that's an example of ideals, finitely generated ideal, and the variety associated with it, and how you may be able to go from one generating set or one basis to a slightly different one. And I guess this is kind of the theme, right? We're going to be choosing or finding a way to simplify these bases in a more systematic way. Linear algebraic methods are not always going to work. It works in this case because the bases are very simple, but in general, we're going to have to do better than that. So, so that's coming up in the next few lectures. So, yeah. So the next definition proposition is going to be about ideals of the ideal associated with variety. So we talk about how given an ideal, and if it's generated by finitely many number of polynomials, you can define the variety associated to that ideal or that basis.
Maybe, sorry to
I'm
interrupt,
going to
Ken.
go backwards now.
Maybe we should make a formal definition along those lines and say, definition: if I is finitely generated, then VI means VF1 through FS for any generating set. By the proposition earlier, that's well defined, and then you can just write that.
Yeah, I think that's a good idea. Otherwise, I'm having to write this mouthful. Okay, so let's write that down. So definition, right? Like if given an ideal equals no, I guess given an ideal in R, then how do we do this? Then the variety associated to I is going to be equal to, I guess this is a finitely generated ideal in R, right? Yeah, so maybe I should say finitely generated. And then VI is equal to V of F1 Fs, where F1 Fs is a generating set or basis of I, and I guess by the previous proposition, by a previous proposition, this is well defined. So whenever you make a definition based on some arbitrary choice, right? This thing here is the arbitrary choice because there can be, there can be many generating sets, as we demonstrated in the previous example, and the previous proposition, previous to the example, it's asking you to show that given an ideal with any generating set, and you define the variety using those equations, they define the same variety. So we're safe in defining V of I as the V of a bunch of generators. Irrespective of that choice, we get the same variety. Cool. So now we're going to go backwards. Backwards, right? So let V, right? So now we're going to start with the variety. So this is going to be a and K, B and. Does the book use affine variety, or did I stick the affine word in there? Like, I get it. Okay, cool. Affine variety. I guess to distinguish it from projective variety. That's right. So you can define. We define the variety associated with an ideal. Now we're going to define the ideal associated with a variety. So I of V. This I looks kind of ugly. I of V is going to be going to consist of all of the elements of R, such that it vanishes on V. Now, just to remind you, this X here is actually X1, X2 to Xn because it's actually a point inside affine n space, right? So it has n components, right? I'm just writing Fx here. And so, yeah, so we're looking at all of the polynomials which are 0 on every point of V, right? And that will give you an ideal. And I think we have
just to nitpick a little bit. I think if we write X here, you were just before talking about X standing for the variables, where here you don't mean variables. So maybe we could use A or something, some other letter anyway.
Is V okay?
Sure. Yeah.
Yeah, let's do it. Hopefully it doesn't look like the big V. But I usually use a small v to denote a point of a big a space denoted by the capital letter. So yeah, so V is not V is the point in V which has n components x1 to xn. Okay, so so we have to prove something, right? So the definition part is like this. So that the claim, right, the proposition part of this is an ideal of R. This is an ideal of R in R, which not of R, in R.
It's actually a little strange to have the hypothesis that V be an affine variety in there, right? I mean, it's true for any subset. Is there a reason why we want to?
Yes. I don't remember why that is. I guess the book is trying to emphasize the duality between ideals and varieties. Right. Yeah, you don't need the affine variety there, right? Yeah, that's correct.
Yeah, I mean, of course, if we want a correspondence between them, then this is an interesting case. But I don't know for the proof we're about to give that it matters at all.
Yeah, it doesn't really use the fact that V is a variety, because all we're doing, as I mentioned before, we're just checking those three properties that addition, multiplication, and 0, right? So yeah, we don't really need the fact that maybe I'll make a note here is that the definition and conclusion, right, that V is an ideal of R does not depend on V being a variety, i.e., it can be any subset. Hopefully that's not too small, it's still kind of readable. Okay, so I will actually prove this one. I am kind of slightly mindful of the time. We're going for another 40 minutes, right? So I probably should maybe talk faster or something. So 0 is in IV because 0 vanishes. The 0 polynomial vanishes on V, right? Because it vanishes everywhere. So this is the 0 polynomial in R, right? So when I write 0, right, it's a 0 polynomial. 2, addition, if F and G are in IV, right? So that means F and G both vanish on all points in IV. Then for all V in V, right? F plus, I'm going to try and fit this on this board. Hopefully I succeed. F, then for F plus G. So when I write F plus G, this is the function, you know, the way you add functions, add polynomials. V is equal to, I guess by definition, it is this. Well, not that. G of V, right? And this is 0 plus 0, and this is 0. And this is what we need to check, right? We need to check that the sum of these functions also evaluate to 0 on V. And similarly, if R is in R and F is in IV, then for all V in V, right, RF, now this time is the product of these two V, then it's just going to be RV, FV, and of course, we don't know what RV is, but we know the FV is 0, so this is RV 0, which is 0, right? So then we checked these three properties, which define what an ideal should satisfy, so therefore it's an ideal of R. So that's the proof. Usually I'll stick a little square at the end of the proof, but that doesn't quite fit. Okay, there you go. Okay, so and so some examples, right? Give me 1 second. I'm gonna have to scroll forward and see how far I'm gonna go with this. Okay, so I'm gonna give I'm gonna give a bunch of examples. I will do the twisted cubic example because twisted cubics are kind of a recurring example in this course. So, but let me give you some simple examples, right? So the ideal associated to the entire affine space, right? So we're looking for polynomials which vanish everywhere, right? And the only one that does that is the 0 polynomial. But this requires that F is infinite. F, not Fk, the field is infinite. So you might want to think about what happens in the finite field case. I'm kind of staying away from a lot of these discussions, but there are any exercises. There is some discussion of what happens over a finite field. If you've got some experience with finite fields, it may be interesting to think about why this condition on K is needed here. So the I of origin is equal to x1 to xn, right? So you're looking for functions which vanish on the origin, or the simultaneous vanishing locus is the origin. So if you think of the n equals 2 case, right? You take the x-axis, you take the y-axis, you intersect them, right? The common locus of 0 is just the origin 0, 0. And so that's it for the n equals 2 case. In general, you get a similar kind of picture there as well. And so the last example is the I of the empty set is R, right? So these are kind of basic examples. Okay, so I'm gonna do the example of the twisted cubic.
Sorry to interrupt, Ken, but maybe we can ask the following question. So when Ken writes I of the set, which is just the origin is x1 through xn, one direction is clear, right? So any the right-hand side is contained in the left-hand side because all those functions vanish at the origin. But can someone say why the left-hand side is contained in the right-hand side? If you have a polynomial which vanishes at the origin, why does that mean it belongs to the ideal on the right-hand side?
So I guess what it means to vanish at the origin, maybe if
Yeah, what are your thoughts? Got it. Sorry to
Maybe-
interrupt you, Ken. So he commented that there's no constant term.
Yep. What are your thoughts is correct, right? So if I is in I or f is in I of the origin, then yeah, so that means that f of x1 xn, right? This is I guess this is, well, sorry, not I of I f of 0 is 0, right? So the origin is maybe I should have said that this is this is 0 0. So then f of a bunch of zeros is 0. So this is really just equal to the constant term, right? So if f, so actually what this means is 0. So yeah, so that's correct, right? It means the constant term is 0. So if the constant term is 0, then right, so then this means that f is in x1 xn. Cool. Thanks for that. So yeah, let's look at the twisted cubic example. So this is actually a interesting example. It's actually slightly involved. So I don't know whether I have time to do all of it. I do want to cover the division algorithm today, which is kind of important for what follows. So I'm going to sketch this without some of the details that I've written down here, and hopefully maybe we can work out some of the details in an exercise session. So I don't know whether, Dan, you talked about twisted cubics last week.
I don't think so.
Okay, cool. So I believe
No, the
that
feedback
twisted
is from
cubic-
you, Ken, but I think somebody else may have their microphone unmuted. Just check, please.
Oh, hopefully mine's unmuted. I wasn't hearing any feedback actually. Is it all right now, Dan?
It was just a little bit. It wasn't a big deal, but I just
Okay.
thought some people might check.
Cool. So, right. So the claim here is that so you have the variety given by these two equations. So it's y equals x squared z minus x cubed. It's inside a three-dimensional space because there are three variables, and the claim is that the ideal of this variety is equal to exactly the ideal generated by these two things. I'll just say that one direction of inclusion is clear, as usual with these things, and we have to spend quite a bit of. Sorry. Oh yeah. Yes. I actually missed this. Thank you. Yeah. So V is this variety here, and I of V is equal to this ideal here. So I'm actually looking at this example, thinking that maybe I'm gonna leave this hanging because I do want to go and talk about the division algorithm, and it's a little bit involved, right? But I will make a comment. That I'm gonna do the thing of say C book for proof that this is often this is not always true, right? You look at the variety, given by some equations, and then you look at the ideal associated with that variety, right? You don't always get the same ideal back, right? But in this case, you do, and so that's good. So in some there in the exercises there are a few examples where kind of obvious examples where when you take the variety associated to the ideal, then you take the ideal associated to that variety, you don't get the same thing back. And I think nilpotent elements is one culprit there, right? So I'll just kind of leave that as a prelude to the exercises. And what I will do is I will write down another proposition, which again I'll skip the proof of because I want to get to the division algorithm. And but this is a fun one. I did say that when you introduce mathematical objects, you have to give some examples, give some methods of construction, and then write down some properties, right? So this is another property one with affine varieties and ideals, right? So let V and W be affine varieties in the same space, right? So n variables, then one, if V is contained in W, so these are, affine varieties are subsets, so you can talk about whether one is contained in the other, if and only if IV is contains IW. So there's a reversion, inclusion reversing. I is inclusion reversing. I guess this is a way to say it. So V is equal to W if and only if IV is equal to IW. Okay, so you're starting with affine varieties, and you can say stuff like this. So you can imagine, can we start from ideals, right? And obviously the previous example, well, what my previous comments indicates that, this is not quite true if you start with ideals, right? You have, but if you start with affine varieties and you look at the ideals associated with them, then yeah, you can do stuff like this. And I think 2 follows from 1, so you only have to prove 1. Okay, so division algorithm. Sorry if it feels like I'm rushing this along a little bit, but I do want to get to this, because if I don't get to division algorithm, I think Dan will be not happy. You might need this. You might need this next week, right? Division algorithm in KX. So the division algorithm is much like the division algorithm for integers, right? So the aim here is to show that KX is a principal ideal domain. I'll kind of say what this is. Domain. I'll put this in quotes and PID for short. By proving the Euclidean algorithm works for polynomials, right? So you may have seen this before for integers. Works for polynomials. Okay, so the Euclidean algorithm here is based on the division algorithm, and so we'll talk about the division algorithm here. So the definition here is that if we're given f equals a0xm, m is now not n, right? So this is different. And again, we're going back to only a single variable, so there are no x1s and x2s, right? There's only x. And the book wants to label their polynomials with a0 in the leading term, so that's fine. I'll stick with that convention, even though I don't really do that usually. So we're going to call this guy, this is the leading term, right? Called the leading term And this A0 is called leading coefficient. And m is the degree of f. Okay. Oh, yes, yes, yes. Thanks. Otherwise, it's not going to work, right? So with A0 non-zero, so yeah. Okay, so yeah, leading term, I guess we also say LT of f is equal to A0 xm. So a bunch of terminology and notations. Hopefully, is relatively straightforward. Degree, leading coefficient, just names for stuff. So proposition, definition, right? So this is going to be the division algorithm. So let G in Kx non-zero. So meaning that G is not the zero polynomial. Every f in Kx can be written as f equals qg plus r, such that either, so q is a quotient, r is a remainder. These letters are kind of suggestive. Either you have no remainder, right? So f is just equal to qg and that's it. Or the degree of r is less than the degree of g. Notice that the degree is not defined for zero, for the zero polynomial. So we have a separate case for that. Moreover, I'll write moreover here. Running out of space. Moreover, R and G are unique. And it's computed by the following. Oh, yeah, yes. I guess my G's and Q's. Yeah, of course, G is unique. Are unique and computed by the following. So I want to make note here is that these uniqueness properties are really nice for a single variable division algorithm. It's not exactly true once we increase the number of variables. So let's walk over. Sphinx of black quartz, judge my vow.
Yeah, I had to look this up. This is the lazy fox jumps over the whatever. It's got all the letters.
Oh,
It's much better than that
I didn't
one.
know this one.
Yeah, this is good.
Fantastic. Nice. Well, I learned something today. Okay, so right, so the this is kind of long, right? So division algorithm is as follows. So the division algorithm, so it takes in G in Kx, and F in Kx, and it outputs, Q and R right there, right? So the algorithm goes, you set Q equals 0, R equals F. So these are the Q and R are the Q and R that we want to output, right? But we set them to be some initial values, and then we do a bunch of steps, and then we end the algorithm and we return Q and R, and that will be the Q and R that we want from the theorem. From the theorem. So while R is not 0, and LTG divides LTR, right? So then we do X is equal to LTR divided by LTG. We increment Q by X, and then we decrement R by GX. Or is that QX? I think it's GX. Minus GX. Right, and so once we're done here, we return, I think this is Q and R. So as you can tell, I'm a Python man, so I kind of indent things as we go. So that's kind of how the algorithm goes. And the claim is that Q and R that we get at the end of this algorithm are the Q and R that we want. So I'm kind of, I don't know whether I have time to prove this actually, but I'm gonna do the proof at the end if I have time. But for now, I'm going to skip it and talk about the consequences. So proof. I'll do this if I have time.
Maybe we can say the one sentence version. The degree drops, and you can check at each step
Right,
that
yeah.
it remains a good expression for f, and there you go.
Right. Yeah. So then like.
Ethan asks.
Sorry
to interrupt. Ethan asks where LT was defined. It was on the previous board. Ethan,
Oh,
so that was leading
it's
to.
defined in the red where I think actually it was in white. The first definition under division algorithm, the leading term is the term with the largest degree, and the degree is the highest, I guess, the highest power of x which appears.
Right, so the leading term is both the coefficient and the power, so it's a0 x to the m in this case. We'll make a much more, we'll come back to this in great detail when we talk about monomial orders, but for now it's only defined for polynomials in one variable. Yeah.
Cool. So yeah, I mean the one sentence thing is the algorithm proceeds by killing terms of f until we get to 0, or until we're prevented from doing so by degree. So each time you kind of decrease the degree until you can't do it anymore, and then the algorithm ends and you get what you get back. And either, well, if r is 0, then it's good, or it satisfies the degree condition that we stated, because it's actually checked by this while loop, right? So whatever comes out satisfies what we stipulated. So the other thing that I would say is that this is similar to the one for integers, right? You just keep subtracting until you can't do it anymore. So the corollary is that 0. Oh, actually, I don't need this corollary, so I'm gonna skip it. Okay, definition. So we say that R is a PID if R is a domain. So sorry for not defining this, but domain just means it has no zero divisors. I guess this means that it means that when you have A and B and you multiply them and you get 0, then either A or B has to be 0. Okay, so it's a domain.
Do we even need to introduce this? All our rings are domains. What you want to say is every ideal is principal, right? Which you can say.
Yeah, we do, but then. Yeah, but then, do we use PID? I feel like PID is a common enough abbreviation and thing that people might wonder what the hell D is, right?
But given that
do they even use it?
R for you is a PID. I mean, is a domain by definition, right? So you could just say like R, which stands for, I guess, maybe I guess it doesn't matter too much, but the point is you don't need to know what a domain is in this course, I think.
Yeah, right. Thanks. So I was going to say PIR, P principal ideal ring, but that felt wrong. Has a singleton basis. Right, so every ideal can be generated by one element, or you say can be generated by one element. That's a really ugly one element. Right, and we always say that the ideal is principal. So these are all equivalent ways of saying the same thing. Some of these have meaning, some of these don't. Like principal is just a name, but being generated by one element, I guess we know what that means. Okay, so all polynomial rings are domains, so we don't actually have to know what that is, and so that's fine. So PI stands for principal ideal, right? So that's it. So proposition is that the Euclidean algorithm described below computes this generator for the Oops, sorry, I skipped something. Let's actually make a definition. A definition, not a definition. GCD stands for greatest common divisor of f and g in Kx is an element or polynomial h in Kx such that 1, h has to divide f and h has to divide g, and 2, if p divides f and p divides g, then p divides h. So this is the same definition as you would have seen for integers. And so I don't know if I mentioned this earlier, but a polynomial dividing another one just means that when you carry out the division algorithm, you get 0 on the other side. Oh, 0 remainder, sorry. Okay. So, well, okay, so I think I have time to write down the division algorithm, the Euclidean algorithm, and we'll see how we go with proof. So, but at least the statement is fine. So proposition. So we define the GCD, right? It's the greatest common divisor of any two polynomials, and we want a way to compute this GCD, and this is the way to do it. It's called the Euclidean algorithm. And again, this is very similar to the one for integers. Defined below. Computes the GCD, right? Okay, so the GCD algorithm goes like this, and it uses the division algorithm. So GCD, right? It takes in f and g, and we want to take the GCD. The output is going to be the GCD of f and g. And you set h, which is going to be the thing that we output. We set this to f, and s, it will be an auxiliary variable that doesn't get returned, but it keeps track of stuff that we need. Okay, so yeah, s is actually going to be the thing that tells us when we are done, right? So s is going to be the thing that keeps getting smaller and smaller, so we check whether it's 0, right? If it's not 0, we do a bunch of stuff. If it is 0, we end the algorithm and we output h. So r is going to be the remainder of f and g, or h and s, sorry. So this is the r term, from division algorithm. So remember, the division algorithm outputs q and r, and this is the r that we want. We only care about the r. And then we set the variables h to be s and s to be r. Okay, so this thing computes the GCD, and so this thing is unique. So the second statement is that so 1, maybe 1, 2 is that the GCD is unique up to scalar multiplication, and scalar multiplication means a factor of k is unique up to scalar multiplication. Okay, so here, if you look at s, right, each time you run this algorithm, right, s is actually set as a remainder of h, or and the previous s, right, or its previous value, and so its degree is going to keep decreasing, and eventually it's gonna be 0, right? So you know, if you have strictly decreasing degree, eventually you're going to end up going to 0. So I think we probably have enough time to write down the proof. So Dan, here's a suggestion from you. Should I do the proof, or should I give an example of the carrying out the division algorithm, or the Euclidean algorithm. Okay, I think that's probably the right way to go, right? So proof is in the book, I guess, but it's similar to a lot of these proofs, right? You have this S, right, that keeps decrementing, and then you just have to just check that the conditions that you want is satisfied at every step of the loop or the while loop, and then the output has the right properties because of the I guess the ending condition or the break condition in the loop. All right, so in book. Okay, so example. I know I haven't done too many examples of carrying out these things, so he's one to finish off. I think we definitely have enough time to do this example, and I can probably talk a little bit slower starting now. So g is equal to x6 minus 1. So so here's an example, and I think I'm just looking at my notes here. So I'm just gonna write down what it is and kind of just say, okay. So it's possible that I actually skipped this example earlier, where this computation was done. But let's look at this plus 0. So this is what you get from carrying out the division algorithm of f and g, right? Yeah. So right. Actually, when you carry out the Euclidean algorithm, right, embedded in there is a division algorithm, and so what we're doing is we're actually taking f and g as in what's described on the previous board, and then writing down the remainder. So this thing here is the R term, right? So this thing here is the R term. Well, let me see. Yeah, this thing here is the R term. So
Are G and F reversed from in the algorithm? So in this first line, you're dividing G by F, right? Whereas, what was the notation for your remainder bracket thing? Was it the remainder of what on division by what?
H by S, right? So yeah, I think they were reversed. I mean, in the same way that when you carry out these the Euclidean algorithm, you have to start with the f has to be the thing that has the higher degree, right? So you go f divided by g, and so yeah, they are reversed. So yeah, I should have written f is equal to, well, yeah, you're right. So the thing that's on the left should be of the higher degree. The thing on the left should be the lower degree. So what you're saying is that this should be 6. Yeah, thanks. And that should be 4. Thanks. 6 and 4. Cool. Okay, then it makes sense, right? So then we go through and we take the remainder, right? And the remainder is x squared minus 1, and then you divide by the remainder, which is x squared minus 1, and then you get 0, right? So and so your algorithm ends on the second line, and so what you output is that x minus 1 is the GCD. So
I think your algorithm on the left-hand side doesn't actually return anything.
Oh shit, you're right. Yes. I forgot return. I think I said it, but I didn't write it. Return H. Yeah, hopefully the H's and R's look significantly different. Like H's and R's are different things. Okay.
They are different. They do not, says Matt.
Yeah, me and my terrible.
Yeah,
I know when Dan writes, all of Dan's letters look distinct. Some of my letters do not look distinct.
Your R is like a
yeah. So when you
interesting one.
It's like a weird cursive R.
I hope you don't have N's and R's in an algorithm.
Oh god. I actually sometimes write R's as the normal way, so maybe I should be mindful of that. Okay, so that's one example. I actually have another example where,
Right, so
I think I'll
the
just say
GCD
this
here
one.
is zero. Is what then? It's x squared minus 1.
X minus 1.
Yeah.
Yeah, and you kind of knew this already because you know how to factorize these guys, right? Like we learned how to factorize these kind of cyclotomic polynomials in high school, and so you know that x squared minus 1 is the GCD. This kind of verifies it when you carry out the division algorithm, multiple times on the various things that appear. So one final comment I'll make, I may not actually do this example, is that if you need to take the GCD of more than 2 elements or more than 2 polynomials, you can just iteratively do them, right? So you can take the GCD of the first 2, get that GCD, right? And if there's a third thing there, right? If there's an H, well, not H, if there's like a K, right? A K is probably also not so good. If there's like a B there, right? You just take the GCD of a B with x minus 1. So maybe what I'll write is that the GCD of f g h, right, is equal to the GCD of f and g. Should have left more room, right? GCD. You can just iteratively do it in pairs, right? GCD of the GCD of f and g of h, and it doesn't matter which way you do it, right? This is completely, agnostic of the order in which you take the GCDs. As long as you've done this, in some fashion, you get the GCD of f, g, and h, and this is just applying the algorithm again to multiple times.
Yeah, I think this is a good example, if I can butt in for a second. So this first equation gives us that x squared minus 1 is in the ideal generated by f and g, and then the so from both of them, from the second one, that's g, right? So this gives you g is in the ideal generated by x squared minus 1. And then if you combine that with the first equation, so you see that this is of course g, so g is in the ideal generated by x squared minus 1, then multiplying it by something is still in the ideal, and that's just adding the thing again, so you get f is in x squared minus 1. So you get that both f and g are in that ideal, and therefore any linear combination of them is in that ideal, which shows you that the ideal generated by f and g is contained in the ideal generated by x squared minus 1. And we have the reverse as well from here, so this shows you that those two ideals are the same, and therefore we've computed what the variety of this thing is, right? Because it's the same as the variety that's computed by this. So that's generally true, that the GCD, so from an algebraic geometry point of view, the GCD is not a kind of prime number thing. It's about, if I give you a list of generators, can you figure out a single generator which cuts out the same thing? And over a polynomial ring in one variable, you can always do that because every ideal can be generated by one thing, and the GCD tells you how to find it.
Cool, thanks, Dan. I think this is a good place to stop. We've reached 3:30 or 10. Is it 10:30 where you are?
Yep. Yeah, that's a good place to stop.
Cool.
Yeah, thanks everyone.
I
Any
think
questions?
next time I do this, I'm gonna have to figure out which things to skip. I almost didn't get through it, which is dangerous.
No, I think that worked out well.
Cool.
Billy, do you put your penguin suit on when you're going to be misbehaving? You've gone from being a...
Why is that voice? Where's that
I
voice
was
come
too told to use it with my normal character, so I had to change.
Are there any questions?